Hello everyone, my name is Mayuka M. Nair, and today we will be looking into the topic of Beer-Lambert's law. Before we jump right into the topic, there are a few terms that are crucial in understanding the law. Now let's look at what those terms are. Now when light strikes a particle, there are three phenomena that occurs. First is reflectance, then it's transmittance, last is absorbance. What are these terms? Reflectance is the proportion of light or other electromagnetic radiation striking a surface that is reflected off it. It basically means how much of the incoming light is bounced back from the surface of a material. For example, a smooth and shiny surface like a mirror has a very high reflectance because it efficiently reflects most of the incident light. In contrast, rough or dark colored surfaces typically have lower reflectance. Next, we have transmittance, which refers to the fraction of incident light that passes through a material. A high transmittant value indicates that a material allows most of the light to pass through, which is a very desirable property for materials used in windows, eyeglasses, and other optical instruments. And lastly, we have absorbance, which is a measure of the amount of light absorbed by a material. Now, when light strikes a material, some of it may be absorbed and converted into other forms of energy, such as heat. Absorbance is expressed in logarithmic units, and this is a very crucial parameter in fields of spectroscopy. Law. Now, as the name suggests, this law is essentially a combination of two laws put together. Let us look at each of these laws individually. Now, Beer's law. This was stated by August Beer, which states that the concentration and absorbance are directly proportional to each other. This is indicated by the adjoining graph, which takes absorbance on the y-axis and concentration on the x-axis. And when we plot the points, we get a straight line inclined to the x-axis, which proves the law. The Lambert's law, which is stated by Johann Heinrich Lambert. Now, this law states that the absorbance and path length are directly proportional to each other. This is again indicated by the adjoining graph, wherein absorbance is taken on the y-axis and path length is taken on the x-axis. And we again obtain a straight line which is inclined to the x-axis by an angle. An important point to note here is that the slope of this graph gives the product of epsilon and C, wherein C is the concentration of the substance and epsilon is the molar absorptivity, which is a constant. We come to the Beer-Lambert's law. Now, before we jump right into the statement of the law, there are a few assumptions that we must take into consideration. The first being, Beer's law assumes that the molecules absorbing radiation doesn't interact with each other. Second assumption, this is applicable for only dilute solutions. And the third assumption is that only monochromatic radiation must be used. Beer-Lambert's law states that for a given material sample, the path length and concentration of the sample are directly proportional to the absorbance of the light. Now, mathematically, it is expressed as A is equal to epsilon into L into C, wherein A being absorbance is the amount of light absorbed for a particular wavelength by the sample. It is a logarithmic measure of the ratio of incident light to the transmitted light through a substance. Epsilon is the molar extinction coefficient or the molar absorptivity. Now, this is a constant that indicates the absorbance of light per unit concentration and path length for a particular substance at a specific wavelength. This value is inherent to each substance and crucial for calculating concentrations in unknown samples. Next, we have L, which is the distance covered by the light through the solution, or the path length. And lastly, we have C, which is the concentration of the absorbing species. There is another formula to represent Beer-Lambert's law in terms of percentage of transmission, and that formula is given by A is equal to 2 minus log of percentage of T to the base 10, wherein T stands for transmission. Okay, the applications of Beer-Lambert's law in real life. First, we have blood oxygen levels. Pulse oximeters, which are devices that estimate the oxygen saturation of a patient's blood, operate on principles derived from Beer-Lambert's law. By analyzing the absorption of light through a patient's fingertip at different wavelengths, these devices can discern the proportion of oxygenated and deoxygenated hemoglobin. Next, you have measuring pollutants. Environmental monitoring often relies on spectroscopic methods based on Beer-Lambert's law to determine the concentration of pollutants in water and air. For instance, the law helps quantify the levels of harmful chemicals like benzene in drinking water or mercury in the air, aiding in compliance with environmental regulations and public health safety. Next, you have food and beverage quality control. In the food industry, spectrophotometry is used extensively to ensure the quality and safety of products. For example, Beer-Lambert's law is applied to measure the concentration of food dyes in drinks and confectioneries, ensuring they are within safe consumption limits. Next, you have atmospheric studies. The law is crucial in remote sensing techniques used to analyze atmospheric gases, particularly in studying ozone layers and greenhouse gas concentrations. And lastly, we have chemical analysis. This law facilitates the monitoring and control of concentrations in chemical manufacturing processes, crucial for product consistency and compliance with industry standards. In attempt two simple numerical problems. The first one is a sample has an absorbance of 0.8 if the path length is 2 cm and the molar absorptivity is 200 liter per mole centimeter. What is the concentration of the solution? The first thing you do when you get a numerical problem is to note down the values that are already given in the problem. Now we have absorbance A, which is 0.8. Then we have the path length L, which is 2 cm. And we have the molar absorptivity epsilon, which is 200 liter per mole centimeter. According to the formula, we have A is equal to epsilon into C into L. The only value that is not given here is C, which we are supposed to find. Now, we just have to do simple substitutions. Just substitute the values of A, epsilon and L, and you will arrive at the value of C, which should be 0.002 mole per liter. The next numerical problem. A student prepared a calibration curve by measuring of the absorbance of 5 standard solutions of a compound at 300 nanometer. A cuvette with a path length of 5 cm was used in the stratosphere. The slope of the curve was 300 liter per mole. The molar absorptivity of the compound is what? Now this may seem like a very complicated problem, but it is not. First thing we do is to note down whatever values are already given in the problem. So we have the slope, which is 300 liter per mole, and we have the path length, which is 5 centimeter. Now, when you plot a graph, when you plot a calibration curve, we have the absorbance on the y-axis and the concentration of the compound on the x-axis. And the slope of this graph is equal to the product of epsilon and path length. So that is the formula we will be applying in this problem. So we have slope is equal to molar absorptivity into path length. So 300 is equal to molar absorptivity into 5. And we get the value of molar absorptivity as 600 liter per mole centimeter. Last but not least, we have our references. Now these are the references that I have used to make this PPT. These references include the content which are present on the slides, the numerical problems, as well as the pictures. Brings us to the end of our presentation. Thank you so much for staying until the very end and listening to all of this. And I really hope you got an in-depth understanding into this topic. Thank you so much and have a great day.